For the second speaker of the April session of the CosmoVerse, we have Nicola Deiosso, and he is a PhD student at Center for Energy, Environmental and Technological Research, CIMAT, at Madrid, Spain. And he's going to talk about cosmological constraints and tensions from DESI BAO and full shape measurements. Nicola, you can start whenever you are ready.
Okay, thank you for the introduction. Again, hi everyone. Okay, today, as my involvement in DESI about tension was more about finding cosmological constraint from BAO and full shape measurement. Today, I want to comment with you cosmological constraints result from BAO data from the ER3 analysis of DESI and full shape from measurements from ER1 analysis. So I will go almost straight to the point. Let me just introduce, okay. Let me just introduce the sample that we used for the analysis. So the DESI data release 2 BAO sample that is composed by 40 million spectra from galaxies and quasar from the first 3 years of observation of the survey, distributed in an area of 10,000, 12,000 square degrees of sky, depending on the tracer that we are considering. This represents a factor of 2.4 of improvement in data volume with respect to the year 1 analysis. As you can see here in the table, we divided the catalog in 7 different redshift bins, spanning from 0.1 to 4.2 of redshift with 5 different kinds of tracers. Bright galaxy survey, luminous red galaxies, emission line galaxies, quasars, and Lyman alpha forest tracers. So in order to obtain information about the BAO feature, we have to compute the two-point correlation function. So we took position and redshift from our 3D map. We measure them, and then we compute the correlation function with the Landis-Sale estimator, locating the excess of galaxies, of objects that we expect to find given from the BAO feature. We have done this analysis in an effective volume of 42 cubic gigaparsec. That is an improvement about 2.3 times respect to the data release 1. And this analysis is made in a blinded way. So in order to avoid confirmation bias during the analysis and during all the tests, all the validation tests, we modified at a catalog level redshift, peculiar velocity contribution to redshift, and also we add weight in order to blind expansion rate, growth of structure, and primordial non-Gaussianities. This is quite different for the Lyman alpha forest catalog because we blind directly the correlation function in order to shift the BAO peak. This is done in order to preserve some features due to metal-like contamination, because if we don't preserve them, we can reveal the direction and the magnitude of the blinding, so we don't want this. And once we have our correlation function, we feed the data to a correlation function of a fiducial model, and we basically obtain information about transverse convex distance and Hubble distance, rescaling our data using these alpha parameters, alpha perpendicular and alpha parallel, and we basically just calculate. We just okay. I was trying to find a precise word, but okay. We just rescaling the data to the correlation function, and from this displacement we can obtain information about the BAO scale. Actually, in the analysis we use this alpha ISO and alpha IP parametrization that allow us to obtain information about the isotropic and anisotropic rescaling of the BAO feature. Okay, let's take a look to the result right now. No, sorry. before that, we have done this analysis considering our BAO and also external data set alone and in combination with BAO. We use CMB data from Planck and from ACT, in the latest case only for the lensing. In the BAO ER3 analysis, the default case is to use CAN-SPEC likelihood, so from data release 4 likelihood from Planck and the lensing likelihood from ACT. Then we use also BBN priors and likelihood in order to, especially to calibrate BAO. We use 3 different supernova samples, Pantheon Plus, Union 3, and DES ER5 catalog. And then we use also this 3 times 2 point and 6 times 2 point information from DES ER3 analysis, including information from weak lensing and CMB lensing. The latest one, DES 6 times 2 point, is used only for full shape analysis. Just a couple of words on the inference. So in the more, let me say, technical details about the analysis, the likelihoods were included in the Cobaya framework. We use Kemp Boltzmann code in order to do theoretical cosmological calculation. And the chains were run, so the inference is performed using MCMC sampler, that is that is already included in Cobaya framework, so it's a classic Metropolis algorithm. And then we derive constraint using getDist module from Python. And the best fit information and the maximum a posteriori is calculated using the e-minuit algorithm. Okay, I think now we can directly go through the result that you obtain. This is our BAO measurement for the 7 different redshift beams. We have in the upper panel the isotropic BAO distance, in the bottom panel the BAO distance ratio, so the ratio between co-moving distance and Hubble distance, normalized with the best ΛCDM fit with our data. That is by this solid line here in the 2 plots. So we detected the BAO feature in all 7 redshift beams. The significance of detection is 5.6 sigmas for the QSO. That is the lower one. And the higher one is for the combined tracer luminous red galaxies plus ELG at this redshift, where the significance is 14.7 sigmas. So that is the highest ever obtained. Let's take a look closer to the diagram, to the plot, sorry. So also here, the solid line indicates the best ΛCDM fit from our data. So ΛCDM actually describes very well our BAO measurement, but we have this discrepancy with this dashed gray line that is Planck 2018, basically, especially at low redshift. Another thing that we can comment on this plot is that, as you can see, the error bars have shrunk from ER1. We have an improvement from 30%, 50%, depending on the tracer. And also, thanks to the bigger data volume, we can also obtain this new QSO distance ratio measurement. Okay. So these are the distance measurements. So let's take a look now to the cosmological constraint, starting from the ones obtained under ΛCDM assumption. So if we consider only BAO, we can just probe omega matter, so the matter density, and this combined parameter H0 RD. So the first thing that we can see is that results are pretty consistent with the one from ER1, fortunately, and but with a 40% more precise result, as you can see here in this contour, in this posterior distribution in the omega M H0 RD plane. And here you can see the result that we obtained for omega M and this parameter. What is the point? That also if we have a bigger data volume respect to the ER1, we have that the tension between BAO and CMB under ΛCDM assumption, instead of relaxing, is increasing. So we are passing from 1.9 sigmas of tension in this plane from data release 1 of results to 2.3 sigmas. So this is the first interesting result from data release 2 analysis, that we have that this tension that favors lower values of omega m and higher values of H0 is increasing respect to previous data. And as you can see here, we have not so far, but discrepancy between these two parameters. And okay, let's try now to obtain information directly on H0, because as I said before, we cannot obtain information directly on H0 when we consider just BAO. If we want information on this, we have to calibrate our BAO considering external information from, sorry, for the acoustic horizon, RD. And we can obtain a CMB agnostic calibration on this parameter considering Big Bang nucleosynthesis prior on the baryon densities. Considering this, we obtain this value of H0, 68.51 plus minus 0.58 kilometer per second per megaparsec, that represent a 28% of improvement in precision respect to the data release 1, but the conclusion is basically the same. As you can see here, we have the same degeneracy direction. We favor higher values of H0 and lower values of omega m, and we have still this 2.3 sigma tension between the two datasets. That is preserved also if we consider an external prior from for the theta star, obtaining also a narrower this posterior distribution here in this plane. So first thing, so we have this tension between ΛCDM and CMB under ΛCDM assumption. So if we have now narrower distribution, we expect that this tension also increase with considering considering SH0ES. So considering ΛCDM assumption, the tension between DESI plus the Big Bang nucleosynthesis prior and SH0ES now stands at 4.5 sigma, and this result is completely independent from CMB measurement. So we have an increasing in tension between SH0ES and our data, considering this assumption. And last but not least, considering supernova, considering the recovered values of omega m, we have a mild to moderate tension from 1.7 sigmas to 2.9 sigmas between DESI and supernova dataset that prefers, as we saw also before, higher values of omega matter. So what is the point? We have three different sources that actually are quite well described, also really well described in a couple of cases from by ΛCDM model, but we obtain different cosmological constraints. So of course this is maybe a problem, but that might indicate that DESI and at least some of the supernova dataset cannot be consistently fit except with models that have greater freedom in the background evolution. And this is why for the ER3 analysis, we put a lot of effort in study the question of state of the dark energy. So we know that for a cosmological constant, the dark energy equation of state is W equal to -1. We can try to examine possible evolution with time, or in general possible deviation from ΛCDM using the so-called Chevalier-Polas-Grinder parametrization that this form where W0 govern the nowadays equation of state and WA modulate the time evolution. It's a pretty flexible parametrization that is good to find some deviation. It's not, I mean, it's just an approximation, but maybe could be useful. And let's take a look on the result that we obtained considering our data. So actually, BAO data alone just define a degeneracy direction. We can't exclude WA equal to 0, so no time evolution at 95%, as you can see here from the contour plot. And also the preference for dark energy evolution is low. We are talking about 1.7 sigmas. In order to have stronger result on this side, we have to combine BAO data with external data. So let's start to this contour that is just BAO. And let's start to include early universe prior from CMB. In this case, we have a more closed posterior distribution. We can exclude now at 95% WA equal to 0, and the preference for evolving dark energy goes up to 2.4 sigma. Still not too strong, but is increasing. And if we consider full CMB information, it's true that posterior distribution remains quite the same. Also, the central values of W0 WA doesn't change so much, but adding CMB lensing information allow us to obtain a 3.1 sigma tension. So we have another increase in tension, but with still this posterior cut at W equal to -3. So in order to obtain a completely closed contour for the posterior distribution, we can obtain it also considering just the DESI data plus supernova data, but the full statistical power of the data is achieved through the full combination, BAO, CMB, and supernova. And as you can see here on the left, but also from the plot, of course, we have that with the full combination, the significance of rejection of ΛCDM goes from 2.8 sigmas for the lower one, Pantheon Plus, up to 4.2 sigmas when we consider DESI plus CMB plus DES ER5 with union free that stand at 3.7 sigmas. And these are the central values that we obtained from the inference. So now this is the same conclusion of the part under ΛCDM. Even with bigger volume of data, we have that this rejection is increasing instead of decreasing, as maybe someone could expect. And now also in the lower case, DESI plus CMB plus Pantheon plus, we are almost at 3 sigmas. So it's not too low, this significance. And it's true that with the ESER5, we are not neither near to 5 sigmas, but is quite tight. It's true also that this preference changes a lot depending on the supernova data set that we are considering. So we have to handle with care this result. Of course, we are not claiming that there is new physics or so on. But as we saw in the previous slide, actually just DESI plus CMB gave us already a 3.1 sigma tension. And another thing that is quite interesting to see is that, as I said before, seems that ΛCDM isn't able to it's good to describe BAO data alone, CMB data alone, and supernova data alone. But for example, let's take a look to this plot. In the upper panels, I know that these plots are quite chaotic. I will try to describe it in a reasonable amount of time. So the black solid line indicate ΛCDM from Planck. So Planck measurement with the gray line indicates the uncertainties at 68%. Also in the bottom panel. In the upper panel, we have isotropic BAO distance, perpendicular BAO distance, and parallel BAO distance. And here on the bottom, we have the supernova distance modulus from the 3 different supernova dataset that we have considered. So, for example, let's take a look to the upper left panel for the isotropic BAO distance. So as you can see here, there is a blue line that is lambda CDM constraint from DESI BAO that actually the fit describes really well the data. But especially at low redshift, we have that our measurement prefers lower distance. And if we try to consider lambda CDM fit considering DESI plus CMB priors, we have this purple line that describe worse in a worst way our data and also Planck. And if we look at this bottom panel, actually this fit isn't able to describe supernova dataset. And this is true also if we consider this orange line that is the best fit of lambda CDM for supernova data, in this case the SCR5, that is that describe quite well this supernova data here in the bottom panel, but isn't able to describe BAO data. If we consider the fit with W0, WA that are this red and green dashed line, this fit allow us to describe quite well BAO data, as you can see here in the top panel, and also supernova data. So with W0, WA, we are able to describe quite well, or better, dataset combination. Sorry, I know that is quite chaotic as plot, but I mean, this is given by the, what is the point? The biggest flexibility of W0, WA allow us to describe at the same time different dataset. So just for concluding for year 3 analysis, what is the final point? That maybe we are not considering some systematic effect from one dataset or another. That is possible. We have to study more on this. We have a lot of work to do on this, but unless this consideration about systematic, it seems that new datasets are not or better, lambda CDM seems to be challenged. I mean, so maybe it's worth to continue studying also extension like W0, WA, CDM. We also can comment about a couple of results that we obtained from the full shape data release 1 analysis, where basically instead of considering just the region of the BAO peak in the correlation function or the matter power spectrum, we consider the full signal. In this way, we can also obtain information about structure growth, and thanks to this, we can constrain different cosmological parameters. So just a look to the fit on the power spectrum for, in this case, 6 redshift beams with a lower amount of data. So with the full shape, for example, we can constrain on sigma 8 parameter. And so also on S8. So as you can see here on the bottom, we obtain quite similar parameter from omega m and H0 respect to the ones that we obtain in the BAO results. And also here we have this 4.5 sigma tension in H0 respect to SH0ES results. Our sigma 8 values are compatible with CMB result, but with bigger errors. And now on sigma 8, we obtain a result that is, as you can see here in this whisker plot, that is compatible with CMB result, but we have tension if we consider S8 results from weak lensing surveys like the SCR3 that prefers also as HSC lower values of S8. Actually, I discovered just a couple of hours ago that this plot is quite out to date because new results from kids seems to alleviate this tension, also considering weak lensing. So we have like another point here from kids now. So Good. And just a couple of words, just for concluding on modified gravity constraint. Thanks to the full shape of the signal, we also can obtain we can constrain deviation from general relativity with the classical phenomenological parametrization nu sigma, where we basically add these phenomenological parameters to the perturbed Einstein gravitational field equation, one that modifies the strength of gravitational interaction and one that modifies the wave potential equation. So let's take a look on the result. If we consider DESI plus BBN priors and spectral index prior, we can obtain a constraint on mu naught that is compatible with general relativity prediction, is around 0 here in this gray contour. If we want to obtain a constraint also on sigma naught, we have to combine our data with CMB data. As you can see here in this plot on the right, we have DESI plus CMB without lensing plus the SCR free times 2-point information, obtaining these central values that are compatible with general relativity prediction that have to be 0, both of two. Just one thing that I want to point is that let's take a look on this plot on the left. As we can see here, the contour DESI plus CMB changes on sigma naught depending on the C likelihood that we use. As you can see here, the blue contour is the standard likelihood that we use that almost exclude the sigma naught at 95%. But DESI plus CMB with illipop likelihood, that is another version, doesn't exclude it. And this tension became also bigger if we consider DESI plus CMB without lensing, where we have a almost 3 sigma deviation from lambda CDM, not lambda CDM, sorry, general relativity prediction. So another point, and now I'm concluding, is that maybe we have to put a lot of attention also on the likelihood choose when we do this analysis, because it seems to give slightly different result depending on it. So we have to put a lot of attention also on this. That's all.
Great. Thank you very much for